onto this computer. Oh, there we go. Okay, that's a yes, it's going.
Yeah, okay, awesome. So as Liam mentioned today, I'm going to be talking about and doing a hands-on demo, which should hopefully go well, about infinite scale Azure DevOps agents using Kubernetes native tools, which are KEDA and Karpenter, to scale private hosted agents. And I'll be walking through each and every step of why we need both KEDA and Karpenter, where the idea came from to us, and how we've ended up using it, and also show you quite an extreme use case, which we'll try and demo today. So who am I? I am Vishal, or Vishal Vazkar, cloud systems consultant at MMT Digital, a cloud architect by profession, and a global cloud architecture lead for Vodafone right now, looking at cloud adoption and cloud architecture across 12 different countries for Vodafone, which is one of our biggest enterprise clients as MMT. But by heart, I'm an architect, a jack of all trades, and do everything with AWS, Kubernetes, CI/CD, Terraform. Used to do a lot of Azure, but just dabbling in Azure these days, because most of my time goes in supporting my clients on AWS. Today's agenda is going to be talking through the need to build this tool, or this concept of using KEDA and Karpenter together, understanding the limitations of what we call as self-hosted Azure DevOps agents, and then introducing KEDA and Karpenter, and then finally doing a live demo, and hopefully the presentation should not be longer than 5 or maximum 10 minutes, and then the rest of the time we'll spend walking through this hands-on demo, and then any questions if you had during the way, while we are waiting for something, for maybe something to scale out, and at the end as well. So what are Azure DevOps agents? Some of you may know, some of you may not. So I just thought that at a very high level, give an overview of what Azure DevOps agents are. So it's a software provided by Azure DevOps as a service. And this software is basically required to queue, build, and release pipelines in Azure DevOps, which is an ALM product. And they can be of two types. They can be Azure DevOps managed agents, which are also called as cloud hosted agents. And they can also be self-managed or private agents, which we have to host ourselves on our infrastructure. And if you think about it, you can use Azure DevOps managed agents, but if you go into the realms of on-premise or into the realms of managing your permissions quite strictly, where you don't want to create things like service connections on Azure DevOps, you may need to fall back to using private agents, which is why there's also that capability that Azure DevOps allows you to use. And they are cheaper in terms of buying parallelism, which I'll talk about in a minute. So our use case for building this tool. So our enterprise clients have many engineering teams. Within our agile engineering teams, some of our enterprise clients use the concept of PIs and using safe, which means that we are distributed across maybe hundreds of engineering teams. And as a result of that, for some of our biggest enterprise clients at MMT Digital, we have clients with over 500 pipelines and going upwards of over 1,000 builds and releases per week. And when we get to this point, it gets really challenging to try and pre-provision or predict how many licenses you would need to buy, let's say for cloud hosted agents, or how many licenses you would need to buy for private agents, and how many private agents would we need to pre-scale to. It all becomes a guessing game in a way, which is not the way we wanted to go, but the way we generally have to go when we don't know the answer to these questions. As an example out here for our clients, that was the case, and we hit that barrier where we had multiple engineering teams, and throughout these pipelines, especially when it came to end of sprints, every team would want to deploy or build their code to try and get their stories approved, which meant that we are having hundreds of builds queuing up at the same time. And what we realized was that there was no native solution for scaling agents on demand, except for an Azure specific one, which is VM scale sets. So we needed a way or a solution that was cloud agnostic, where we could host this on AWS or Azure or GCP or on-premise, wherever it was. And although we found a way, which was the private agents, we either ended up over provisioning and wasting a lot of money for the provision infrastructure, and also for the parallel licenses, or under provisioning, which meant that we said, oh, we are only going to have 50 agents. From what we have seen, sometimes we need more than 50, and that sometimes is almost every day at from 11 a.m. to 2 p.m. And because we have under provisioned our agents to maybe 20 or 50 agents, everyone else coming in the queue would have to just queue up and wait for all the other builds to go through, which can get really frustrating as an engineer. To give you a very simple example, if you have an application built with .NET Core or with Node, and as a developer, you almost got it right, and you just want to build and check whether your unit tests are passing, so you trigger a build. As a part of the build, you figure out that, okay, some of my unit tests failed, or maybe some Sonar Cube analysis failed, and I know what the fix is. I want to quickly fix it and quickly test it again. But now suddenly you're at the back of the queue and you have to wait for all these 50 builds to go through. And as unrealistic it may sound, it definitely happens on clients who are building and releasing very frequently and don't have this capacity at them, really. So that was our challenge, where developers and engineers had to wait for build queues for a long time, which increased frustration in engineering teams. So we had engineering managers coming to us as a systems engineering team and saying that, Vish, people cost is higher than infrastructure cost. And for every person we are waiting, if it's a contractor resource, we're paying hundreds of pounds a day, and they're only able to build 3 times a day, as an example. And if we provision a couple of more VMs, surely that's going to be cheaper. And we had so many people coming to us that way that we had to pre-provision, and thus ended up in over provisioning. But another quite interesting challenge that we had was that we had built a one size fits for all, because we are hosting these private agents, and now we need to support .NET Core, .NET, Python, Java, Node as projects. We had to get all of these tools installed on our Azure DevOps agents, or have steps which would install them on the fly, which would then also add some time to our build and release phase. And what that meant is that Docker images started getting really big, and it got to a ridiculous point where a single Docker image was, I think, something like 15 gigs, because it has .NET, Java, SQL, and all sorts of things installed on there. So it got to a point where it was no longer a Docker image, but it was like this monolithic VM that we are packing into a Docker file. So we needed a solution for that. So our initial solution was, let's go and try and find something, and we found something called as KEDA. So what is KEDA? KEDA is Kubernetes event-driven autoscaling, and it's a CNCF initiative. And for more information, you can read it up on keda.sh. But at a very high level, if I show you what CNCF is, it's basically hosting or an ecosystem for all cloud native software. And for people who have not heard about it, some of the biggest projects like etcd, fluentd, Kubernetes, Helm have come from CNCF. And as a part of that, we keep following what new projects are coming up, and they sort of come up in 3 different stages, which is sandbox, incubating, and graduated. And we realized at the time that there was a sandbox project, which has now moved on into incubating because people are adopting it more and more. And that was KEDA. And I'm going to try and move this down here, sorry. So what KEDA is, as I mentioned, it's a Kubernetes based event-driven autoscaling component. So for those of you who know Kubernetes, you have a concept of horizontal pod autoscaling within Kubernetes, but KEDA is baked around it, and it is event-driven. So what they have is a concept of scalars, and within this concept of scalars, you have different types of scalars, where you can scale for RabbitMQ. You can scale for application insights using Datadog, InfluxDB, and many different tools. And they have their own integrations directly into these tools. And one of those tools, while doing our research, we found was Azure Pipelines. So what KEDA allowed us to do was to release this Kubernetes native CRD, or custom resource definition, that would poll our Azure pipelines every as many seconds as we like. And if there was a queue, it would basically create a new pod, which would be a new agent. And once that agent is done running, it would basically terminate that pod, and then wait for that agent pool to have a request for an agent again. And from our point of view, that was brilliant. We're like, great, we found a solution. So we went and looked into it, and it worked. And I'll show you how it worked as a part of the demo. But it still didn't answer all of our questions. Oh, not sure what happened there. You can still see my presentation. Yes.
Yes.
Yeah. Okay. Awesome.
Yeah.
So it did solve a part of our problem, where we found a solution where we would potentially be able to scale out Azure DevOps agents whenever there was a queue in our build pipelines. But it didn't solve the complete problem. And that problem was that the agents would scale seamlessly, but these agents need to sit somewhere, and that would be EC2s in AWS world, or VMs in on-premise or in any other cloud systems. And these underlying VMs would not scale as quickly. So if there was a request for 100 agents, KEDA would just put those 100 agents in within a matter of seconds. But then those pods would all go into a waiting state because it wouldn't have the underlying compute like CPU or memory. And then it would have to wait for something like the cluster autoscaler on Kubernetes to trigger a VM deployment, and that VM to be ready. And then on that VM, these pods to be provisioned. And thus long queues was still a problem. And we had to still wait for upwards of maybe 5 or 10 minutes. And although 5 or 10 minutes doesn't sound a lot, in active development, when people are trying to actively release constantly, it does get very frustrating, even you have to wait for 10 minutes. So although we were happy, we were not content that KEDA would solve all of our questions. So we kept hunting for, okay, how can we solve this issue of scaling VMs on demand without having to rely on cluster autoscaling, or without having to rely on a ticking mechanism where we are basically having some sort of a cron job where it checks whether I need to scale and then provisions VMs. We wanted something which was reactive rather than like proactively just having some cron job in place, like the current AWS autoscaling or any other autoscalers that we see on our cloud providers. So introducing Karpenter, and I love how all these tools start with the K because they are in Kubernetes, but introducing Karpenter, and we came across something called as Karpenter, which is a just-in-time node autoscaler, and it replaces cluster autoscaler and is quicker and more efficient. So it's real time because it's Kubernetes native. I say real time, it's near real time. And it uses a wide range of instance types. So this is where the game changer was, that generally when we use auto scaling, you would have to specify what type of instances you want to scale. So maybe DV2 large or extra large, or C5 extra large, or T3 mediums in AWS world. We normally have to specify the instance types, but what this autoscaler did is removed that requirement completely. The way it has been built is it provisions a VM based on the resource requirement. So as an example, if half a CPU was requested, it'll provision a T3 small instance type. And if there was a higher requirement for 4 CPUs or maybe 10 CPUs, instead of provisioning 20 instances of T3 small, it will provision 1 C5 large and complete that demand. And we had never seen something like this before. It was basically like something completely alien to the auto scaling world within AWS, at least to me. So it obviously caught my interest, and we started looking into what this is. And the best part is that it's native to Kubernetes, so it's not built for one cloud provider. But currently, it has only onboarded one cloud provider, which is AWS. but it has plans to onboard all cloud providers in the future, where it hooks into node autoscaling for AWS and GCP as an example, so Azure and GCP as an example. So just to show you again at a very high level what Karpenter is. As I mentioned, just in time node autoscaling, and it is basically what I mentioned. So if there are some pods that are pending to be scheduled, Karpenter evaluates how many nodes we currently have and how many nodes we would need, and what is the right size of a node that I can give so that I don't have to provision many of those. So it does both vertical and horizontal autoscaling based on the logic of requests from Kubernetes, which is very, very interesting. So we thought that, okay, we can potentially combine Karpenter to do the underlying VM autoscaling and KEDA to do the agent autoscaling. And if we can try and pair these two tools up, we may have a solution that has never been built before, and that can actually work for our case. So we invested some time and ended up coming up with this solution, which actually worked for us, and was a combination of KEDA and Karpenter. So that's what my demo is going to be today. So I'm going to be using AWS to deploy an EKS Kubernetes cluster. I'm going to use KEDA to scale our Azure DevOps agents on demand. I'm going to use Karpenter to scale our underlying VMs so that whenever our agents scale out, we would have the underlying EC2 capacity scaling out. And at the end, we're going to try and, or during the demo, we will try and do something extreme, which I haven't tried before, but I might go horribly wrong. But what's worse than failing on a live demo? So we'll give it a go anyways. And try to trigger 100 builds in parallel when we have 0 agents available, and then see how KEDA and Karpenter react to that and what happens in the background. And I must admit, I've tried to do this with 20 or 30, but let's try to do it with 100 and see what happens. So that's the demo. And one point I missed from here is we'll also be using something called as AWS Bottle Rocket. And what AWS Bottle Rocket is basically a VM type, which is an open source VM built by AWS, which is a minimalistic VM which only can host containers. So it's stripped down to a point where it does not even have a terminal on these VMs, and it's secure by design. And the advantage of it is because it does not have any of the other packages, the provisioning time of these VMs is rapid. And hopefully, if everything goes right, then these VMs should get provisioned within 30 seconds and get ready within as compared to any other VMs that we would generally provision would take at least a couple of minutes to provision, and then it would get the Kubernetes runtimes on it, and then we will be able to provision pods. So let's see how that works, and that's something I'll show you along the way. So appreciate that's a lot of talking, and as I mentioned, I'll try my best to keep talking to a minimum for PowerPoints and go into the live demo. So just before we start the demo, if I was to cap this to maybe a couple of minutes, did anyone have any questions before we start? No?
Nope.
Okay, awesome. So let's start then. So what I've got out here within AWS, apologies, I've called it .NET Knots. It was just purely decision made in haste where I've done multiple of these. So instead of DevOps Knots, I've called my cluster .NET Knots. But what I've got out here is an EKS cluster, which I've provisioned already right now. And that's the only thing I've pre-provisioned. Everything else we'll be creating on the fly, because creating this cluster generally takes about 20 minutes, and I wanted to save that time. On this cluster, we currently don't have any of the KEDA stuff installed, and we only have one worker node, which is hosting basic things like core DNS, kube proxy, AWS node, and things like that. And there's nothing that has been specifically tweaked on this cluster. So this is a basic EKS cluster. All right. So what we'll do is we'll basically first go to this terminal view, and I've got four views out here, which we will use soon. On the top left hand side, I have pods, which should show us all the pods that come up and scale down. Below that, I've got all the nodes, which are the EC2s or the VMs. Next to that, I'm going to open up some logs so that we can show you the logs of what is happening in KEDA and Karpenter as we go along. And out here, it's just a miscellaneous terminal that we can just keep doing what we need to do, like installing our Helm charts or any of our Kubernetes manifests. Cool. So what I will do first is on our Helm website, we can find a chart for KEDA. And if you search for KEDA over here, you should be able to see that there is a KEDA operated chart and how to install it. But I have got the command over here, and I'm going to install that onto our Kubernetes cluster. Awesome. So as you can see out here, we have got the KEDA operator and the metric server. The metric server is what actually has the metric for Azure DevOps, and the operator is the CRD in which we will then push the KEDA controllers, which then poll the system. So on the bottom right, as I mentioned, for logs, I can now go into the operator and see what's going on out there. And as you can see right now, it's just starting the worker. It's not polling anything, and it's not doing anything special right now. So moving on, what I'll now do is I will install the KEDA jobs on there. So before I do that, I'll just show you our agent pool. So again, out here, honest mistake, or maybe keeping it consistent, so deliberate mistake, to call my agent pool .NET Knots demo. But out here, as you can see, that's the agent pool that I have in our Azure DevOps agent pools. And currently, there are no agents out here. And I've also got a pipeline. So what I'm going to do now is install some agents over here, or at least have this agent pool activated so that it can accept jobs. And by default, Azure DevOps has a rule or a setup where if you don't have any agents on an agent pool, by default, it should just fail. So there you go. It has failed, and it said no agent found in pool.NET Knots. So what we're going to have to do is deploy a placeholder, which is disabled, and then deploy the scaler, which takes care of all the scaling. So I have got both of those now. So let me deploy the placeholder first, which will be disabled by default. So I've got the KEDA scale deployment. So I'll do that. Apply. And while that is happening, I'll show you what that deployment is. So by going into KEDA scale deployment, we have got a base64 encrypted secret, and we have got a type deployment, which is the Kubernetes deployment. And that Kubernetes deployment is an Azure DevOps agent with one replica. And that's going to basically use my agent pool out here and deploy that agent. And I've also pushed the Docker image to a repository within AWS, and it's going to use that. It's going to use that image to get this agent. And as I mentioned, we don't want to scale this deployment. We just want to keep it as a placeholder because of that Azure DevOps limitation that we need to have at least a disabled agent out there so that we can pick up these jobs. So let's see what has happened in the background. So going back to .NET Mouse demo. We haven't got anything out here, and that will be because, as you can see over here, our Azure DevOps deployment is in a pending state. And this is a typical example of you provision an EC2, but you predicted it wrongly that EC2 is going to be enough to meet our compute demand, but now it hasn't met our compute demand, and now we are stuck because there are going to be loads of pods or agents waiting to be queued up, but we don't have the underlying compute. So this is where I'll deploy Karpenter, and I'll show you how it has been set up. So within Karpenter over here, we have a Karpenter provisioner, and it is a 23-line file. So as I mentioned, quite straightforward in terms of how you can set it up natively in Kubernetes. But what this does is it provisions spot instances. So for those of you who are new to AWS or don't know what spot instances are, they are basically VMs which are provided by AWS for up to 70 to 80% discount in terms of pricing. But the disadvantage of it is that they can be revoked at any time because they are spare capacity within AWS. But because we're using it with a native autoscaler, even if they are revoked, we can still provision new spot instances, and this logic has been baked into this custom resource definition. And to go into a little more complex details out there, for those of you who have used AWS to a more advanced level, it also uses something called as a confidence score. So AWS last year launched a confidence score on spot instances, where it would check on a confidence score from 1 to 10 of how likely your VM is to get revoked in this zone. And if your confidence score is 1, it would mean that you would probably get a revocation on the same day. But if your confidence score was 9, it would probably mean that maybe for the next 2 weeks you're good, where you're very unlikely to get a revocation on your VM. So this tool uses that logic baked into the Karpenter logic, where it uses a high confidence score and it only provisions these instances which have a very high confidence score based on the request, and also looks at what is the closest match. So very, very intelligent, and I think you should read about it a little more if that is
specify
interesting.
then, Vish, is there a configuration where you can tell it what confidence score you want to use above, or is it just automatically baked in? That
automatically. So it automatically looks into it. So yeah, we don't have to specify anything for that. And to go into AWS very quickly and show you what I mean by that, I will go here and show you. So in EC2s on AWS, on the left-hand side, you should be able to see spot capacity and spot requests over here. So if you go into spot requests, you should be able to see on the right-hand side spot placement scores and pricing histories. So pricing history is where it tells you how much cheaper you're getting your VMs for. So let's say a C3 large is for 74% cheaper than normal cost, as an example. But if you also look at placement scores, then you should be able to put a region, let's say EUS 1, and calculate placement scores. And you can see that the placement score is 9, which means that it's very likely to give you those instances. And then you can further go and edit and see the capacity and instances of what types of CPUs you want, what types of VMs or architecture on your VM you want, and it will give you your placement score for each instance type. So it's a very helpful tool. But what Karpenter have done is that they've baked in this logic while they get this instance as well. So yeah, it's very, very intelligent, and I just thought I should mention it just for those who would get a little excited like I do about these placement scores. So cool. Coming back to our current situation, we tried to deploy an agent, but we didn't have the underlying compute capacity. So what I'll try and do quickly now is deploy that Karpenter CRD, which I showed you right now. So let me go there and Karpenter provisioner. And in the background out here, I'll go into Karpenter. And as you can see, now that I've put the provisioner on, it checked that it needed one node. And in the background, it's already gone and provisioned an EC2, the red one out here. And just to explain what's happening in a matter of mere seconds, it has gone and it has made a spot request. It has got an approval on the spot request to get that VM for a cheaper rate. It has then gone in and got the EC2 instance, and it has provisioned that EC2 instance all in a matter of 1 second. And it all does this via native integrations directly from a Kubernetes native workload into AWS, which is super duper powerful. So what I've got right now, as you can see, is a VM getting provisioned because there was a pending pod. And as a part of that VM, we are using Bottle Rocket, as I mentioned, as an AMI, as you can see out here, the one that I've highlighted. And in terms of instance type, you can see from the spot request out here that it is a spot request. So the instance that we have currently, that instance ID is actually 75 up to 75% cheaper than what it would generally be, which would potentially be in pence. So going back out here, another low level detail out here is generally when you work with Kubernetes and when you work with cluster autoscalers, your cluster autoscaler would wait for your node to be up and running, and then it would go and provision all the resources on that node. But by using Karpenter, it does the opposite. It says this node is going to become available, so I'm going to already put all the pods on there, so that whenever the node becomes available, it is instantly going to bring up all the requirements that I need, and I don't need to wait for an event back to say that the instance is ready. So that's another out-of-the-box functionality that is provided by using Karpenter for our node autoscalers. And as you can see right now, it's taking a little bit of time, and I don't necessarily know why, but it looks like that instance is taking some time to come up, and it's now up. So you can see that the instance is healthy, and it took 2 minutes 30 seconds for the instance to be healthy. And now on the top side out here, you can see that the Azure DevOps container is creating, and it's waiting for the container image to be pulled down from ECR. In general, Azure DevOps agents are at least 1.5 to 2 gigs in size because of the nature of the agent. It's on a full fat Ubuntu image, and it has some really heavy tools like Azure CLI that are installed on there, which take up another gig as well. But as you can see out here, you now have this Azure DevOps agent placeholder. And if I go to my agent pool, you can see there's a deployment that is online, but it isn't enabled because we just want to put it on as a placeholder, and we want our scaling objects to take care of giving us agents. And I'll talk about that in a minute. So a lot of moving parts, but we got it working. So what did we do? We provisioned KEDA. And through KEDA, we deployed a placeholder agent so that we can trigger builds. When we did that, we realized that our current EC2 did not have enough capacity, compute capacity, and there was no way of giving more compute capacity because there was no autoscaling mechanism which was quick enough. So we went back to Karpenter and provisioned the Karpenter autoscaler, which takes care of giving you instances on demand. And then that stabilized the Azure DevOps placeholder. So finally, what I'll do now is I'll go back to KEDA, and I will deploy something called as the scaled object, which is scale job, which is what does the autoscaling. So to show you the scale job very quickly, what what I've specified out here is that on one particular EC2, do not provision more than 10 more than 10 agents, because if you imagine, if you get one instance with 20 agents, and if all of them are trying to do an npm install at the same time, you're going to kill that EC2. So you can control things like those by using topology spread constraints, and case by case basis. If you have build agents, you can have a maximum of 1 or 2 agents running on one VM. But if you have release agents which are merely triggering Terraform apply or doing some cloud formation updates, or maybe some ARM template updates, then you can increase that skew because they're not very CPU intensive, and you can control that using topology spread constraints. And for those of you who want to play with this logic, I also have an open source repository on GitHub, which is called as a POC collection. And in there, I have this KEDA and Karpenter logic, and within the source and on a little getting started guide. And you should be able to get started using it both for Karpenter and KEDA. This is not a secure Kubernetes cluster, so it will be an open Kubernetes cluster, but you can have your own Kubernetes implementation, as this is just a POC. So going back to the jobs, node selector is where this pod will be provisioned, and we want to provision these nodes only on our spot EC2s, not on any other EC2s. And then this once flag is basically an Azure DevOps functionality, where Azure DevOps agents get terminated once a single agent has deployed. Once a single build has deployed and completed. So think about it as though if we were to run an npm install and an npm build, and it does a lot of things where there are some artifacts generated and our build is completed. And if our developers have forgotten to clean up, then we don't want the next build and release to be polluted by this. And the way to do that was by using cleanup mechanisms within pipelines. But if people forgot to use those, then they would generally see discrepancies or unexpected behavior. The way to avoid that is by using a once flag on your argument when you spin up an Azure DevOps agent. And what that does is that agent, once it's done doing its job, it gets terminated and it gets reprovisioned, so that the agent is a clean agent and does not have anything hanging around from the past. So we thought that that's helpful, so we have added that out there. And then we have generally the agent pool name, Azure DevOps URLs, the path token, the polling interval of how frequently we should be polling the pool. Right now it's 10 seconds. And then the max replica count, where how many replicas should we scale out to. So if you don't want your builds to go very high, or if you don't want things to get misfired or mistriggered, you can also configure what's the max limit of your agents that they should be scaling out to. But you can also configure Karpenter to say, don't give me more than 100 CPUs because that's going to make my bosses upset, or that's going to give us a ridiculous build that we didn't expect. So you can control how crazy this can go, and that can be done by limiting the number of resources that these tools can actually provision. So that's what we have done out here. And then finally, this is the CRD, or this is the final part, is the scaler that KEDA has built, which gives us those agents. So let's deploy that and see where we get to. All right. So kubectl apply scale jobs, and in the background you can see that it didn't create anything new, but it went into that CRD, and what it has now done is it's now polling that agent pool to see, are there any jobs pending? Are there any jobs pending? And it's doing that every 10 seconds. And what we'll do in the background is now we'll go and we'll trigger a build manually first. So out here, I can go and show you what my build does. At this point, it does something very simple, which is it sleeps for 60 seconds. And then that's what it does. So let's run that and see what happens in the background. So we're running that. It's in a queue. As you can see in this agent pool job, you can see this queue, and it started 5 seconds back. But what's happening in the background if I would have got my tabs right over here, this scaler figured out that there was something pending and instantly went and provisioned a scale job. And that scale job got provisioned in the background. I should really be better with this. Sorry. In the background, as you can see, that build is already running. And in our agent pool, we got one new agent that is running the build. And the wait time for that was 11 seconds. So our development team had to wait for just 11 seconds for a new agent to come up and a build to get triggered. And it just works out of the box. And if you go back to our terminal, you can see that there wasn't a need for a new VM because there was already a VM that could handle the capacity that was requested. And just to show you, the capacity requested out here was half CPU. But if you have build agents that need a higher CPU, then you can also increase this to say our build agents need 2 CPUs, and then the request to Karpenter would have been 2 CPUs instead of half. But in this case, half is enough because all we're doing is sleeping on our build agents. So yeah, that's that. But one interesting thing out here is now that the build has been successful, that agent is gone. So you can see within the jobs that build was successful and it completed within a minute because we had a sleep for that amount of time. And once that was done, the agent was deleted and it's gone away. So that's the benefit of using this solution, is that it just scales on demand to as much as we like. So let's try to go at a medium example, or maybe a little higher amount of agent pools, right? So let's say 10 and see what happens out there. So, or maybe 5. Let's do 5. And then I've written a script which basically will go in and it will trigger the same pipeline 5 times, but try to analyze this as though 5 different teams trying to request for build agents to build their own pipelines. So I'm going to try and simulate that, and let's see how it goes. So I'll trigger bulk deployments, and what it's doing in the background is it is queuing these up. So you can see 1, 2, 3, 4, 5, but there aren't any agents. But as you can see out here, within a matter of merely seconds, we've got 3 agents up and running. They've picked up the jobs, and 3 out of these 5 are already up and running, and they had to wait only for 13 seconds. And you can see that 2 of them have not come up because our EC2 did not have the capacity. But in the background, Karpenter took care of that, and it went and it provisioned an EC2. And that EC2 is now getting provisioned on type spot. So if we go back to AWS, and if I refresh, we should have another EC2 that's come up, which is T3 medium. And all of this happened in a matter of merely seconds as we were talking. So we scaled out on Azure DevOps, but we also got an EC2, and everything just worked natively within Kubernetes without us having to wait for any AWS autoscaling group to get triggered. So let's see how long this instance takes to come up. But in the background, let's try and scale this out further. So I'll tweak the script, and as I had promised, do an extreme example of 100 builds. So I'll try and queue up 100 builds and see what happens. And this is where it might all work, or it was nice speaking to you folks. So there you go. Have triggered that script. It's going to go in and trigger 100 builds. So let's see what's happening in the background. So yeah, as you can see, it's going in and adding a queue of 100 builds out here. And in terms of agents, we don't have 100 agents, so it's all just queuing up. But from our terminal, what we should be able to see is, from a pods point of view, they're all pending because they're waiting for EC2s to be provisioned. And they are going to wait, and there's going to be 100 of them that are going to be waiting because we don't have the capacity. But what's more interesting is that in the background, if you go into nodes, you can see that we have also got the EC2 instances or the VMs that have scaled out. And what's more interesting is these VMs are not of size T3 medium, but they have automatically picked of size C5 2x large because I have capped it to only having 10 agents of half CPUs each. So it found C5 2x large having 4 CPUs which can run 10 agents. So it calculated all that math and gave me 3 instances of C5 2x large, a couple of instances of C5x large, and a couple of instances of T3 medium, all of type spot. So all of these instances that have been provided are like up to 75% discount. And all of this happening merely in a matter of seconds again, from what we had spoken about last time. So that is the power of using these two tools together. But what would be really key out here is to see whether all of these pending jobs and pending VMs actually stabilize. So based on our last example, it looked like it took about 2.5 minutes to stabilize. So I'll give it 2.5 minutes, and that'll be 2.5 minutes for any questions, quick questions if you had while this is stabilizing.
Have you done any calculations on cost savings?
Absolutely. So we have done calculations as well as used the AWS cost calculator. And it depends on case by case basis. But for some of our enterprise clients, we would be saving upwards of tens of thousands of pounds per month because of merely over provisioning and pre-provisioning agents that they had to do. And with this use case, it would just work it out for them when and if required, and otherwise it would not be running anything in the background.
And for the pods, can you use custom AMIs?
Yes. So again, giving an example of some of our enterprise clients, they have security approved AMIs, which get baked in with all the security approved tools for EKS, for ECS, and for any workloads. All we have to do is merely pass in our own AMIs instead of passing in Bottle Rocket, where we did, and out here, and we're ready to go. So you can have your own launch configurations with your own user data, with your own AMIs, and it'll use those instead of using Bottle Rocket.
I think there's another consideration as well on top of that, where if you're buying concurrent jobs like the Microsoft hosted ones, for example, you couldn't do the sort of scaling that Vish is doing now. I think it caps out at 20, and that is £609 a month that you're paying for it just to kind of sit there. Whereas at least with what Vish is doing, is you're not going to be paying for it if it's not running.
Yeah. And then overall people time as well, because there's going to be no queues. There's not going to be any engineers waiting, and it's going to actually empower our engineers to build and release more often. So that is a lot of people time that you're saving as due to this. So as you can see, today I'm a lucky man because all of these EC2s are now stabilizing. And on each of these EC2s, as you can see, these pods are now starting to stabilize and run. But one thing to notice is because this time around we had EC2s that had to come up from scratch, our pipelines didn't get provisioned in seconds, but they had to potentially wait for a couple of minutes. But within a couple of minutes, so within 4 minutes out here, we have 100 of our builds that are getting queued up and that are running, and nobody had to basically wait beyond that point. So and if I go onto our agents tab out here, you can see that we have got loads of Azure DevOps agents out here, and they're running the builds, and as the builds are getting completed, they are going offline and they're getting kicked out of this agent pool. And overall, we are scaling to meet demand, which is the most important part. So at a very high level, that's what the combination of these two tools do. What I'm going to try and do is wait for these jobs to get completed, which will potentially take another 1 minute, because there's a 1 minute sleep, and then requeue them to show you how you don't have to subsequently wait for 4 minutes. It's just the first time that we had to wait for 4 minutes, but any subsequent triggers would have the EC2s out there, because what we have got on Karpenter is a cool off period. Because we get charged per hour for our EC2s, you can ask Karpenter to have a cool off period of either 5 minutes, 10, 15, 20, or maybe even an hour, so that once the EC2s are provisioned, they do not get decommissioned for maybe 55 minutes. And that means that once they are up, you're going to get charged for an hour anyways, which is going to be in a very minimal cost. But it also means that you can just leave it out there for an hour, potentially, and any new builds will just be provisioned within a matter of merely seconds as compared to 4 minutes. So let me try and demo that very quickly once all of these jobs are completed. So there you go. All of these jobs are now completed. And if I go into agents and if I refresh, all the agents are gone. So we just demoed 100 builds getting triggered. We're scaling to demand for 100 builds. And then we are basically scaling back down. So the cost benefit of it is maximum to us. And just to prove what we're talking about again, let's trigger that script again. So so there you go. So we've triggered it again now, and let's see how quickly these come up. So going back into Safari, in jobs, you can see these builds have already started running, and the wait time was 9 seconds instead of 4 minutes. So as I mentioned, like the first time for the actual nodes to come up, it takes 4 minutes, but subsequent builds for the next 45 minutes till the actual EC2 gets decommissioned, they will be within a matter of seconds. And if I go into agents out here, you can see all the 100 agents are already back up, and they've already picked up a build. They're already running builds, and once the builds are done, they're already getting terminated. So we are basically scaling in real time, not only the agents but also the EC2s. So that's the power of using these two tools together that we have unlocked by identifying and grouping these two tools together. So yeah, if I refresh this, you should be able to see all 100 jobs queued up, and the wait time for each of these jobs roughly was around 10 seconds. And we didn't have to get in touch with any systems engineering team. We didn't have to wait for AWS autoscalers to kick in so that it gives us EC2s. It was all taken care of on demand. And we have happy engineers and we have happy systems engineers, and cost-wise, we are basically mitigating pre-provisioned resources out here as well. So while this is running, again, it's not going to do anything special. It's just going to run these jobs and then finally terminate the agents after the jobs are done running. So I also wanted to show you where finally how the EC2s get terminated, but that'll potentially take another 10 minutes because of the cooldown of 5 minutes that I have. So I would like to use those 10 minutes for any questions or anything that you would like to ask me in the meanwhile. And then what I'll do is I'll reshare my screen and show you how those instances were terminated.
Sure, I've got a quick one if possible. I'm
Yeah.
not sure about the interplay with Karpenter and Spot instances. Does that fix the problem of Amazon ripping away your Spot instances because they have other requirements for them? It will go and try and create that, 99th image, 100th image, etc. for you, or do you still have to handle those deprecations yourself?
Yeah, so it'll take care of it. So generally, just to give you some background of what happens when Amazon asks for a revocation, there's an event that gets sent into something called as event bridge, and you have 2 minutes to react. So within those 2 minutes, you either consume that event and bring up a new EC2, and that is handled by Karpenter. So whenever there's a revocation request, Karpenter just knows about the revocation request. It'll go and see what's the next matching highest confidence score EC2, and it will provision that.
So using this system, you've got, the usual delay when you've suddenly got load on because something's gone out and loads of customers are now coming to your site and there's heavy load. So if you do this method, you've already built your instances that normally take that first 4 minutes or so, and then you remove them, so you're not paying for them, and then they'll just quickly spin up in
Pretty
seconds when you need them. So you can scale up to 1632 or whatever instances, strip them down so you haven't paid much, and then when the busy times come during the day, you've already got that image ready to go.
Yeah, and then you don't have people waiting out there to figure out which instance type you need or how big of an VM you need. It figures itself out based on the demand. And in this case, the use case is specific to Azure DevOps, but you have different scalars. Like, as I mentioned, RabbitMQ, if your queue size goes up, then it'll scale based on queue size. So it depends on whether you would like to use KEDA and Karpenter together, but you can also decide on using Karpenter independently within your Kubernetes workloads to provision your nodes. The choice is yours. In this case, we've used Karpenter and KEDA together because it fits our use case, but both of these tools have been built to be used independently if required as well.
Thank you.
No worries.
Hey, Vishal, just a quick one.
Yeah.
How you're taking care of different agent image types of the agents in this deployment?
Yeah, so currently we have one image type, which is the general Azure DevOps image type, which we have. The advantage of using KEDA is that you can have as many image types as you want built as Docker images, and you can have KEDA scale multiple KEDA scalars. So you can have one job which is pointing to agent pool which only takes care of Node, one agent pool which only takes care of Java, one agent pool which only takes care of .NET Core, and all of these agent pools are powered by KEDA, and KEDA is running on an EKS cluster which is powered by Karpenter. So it'll just work itself out, and you can have as many different types of agent pools as you like, and split it out that way. But currently, I only used one type because we were only showing how to use KEDA. But you can split that out and have multiple definitions of scale jobs.
Okay, thank you.
No worries. Any more questions?
There's a quick one in the chat for you, Vish, from Rajesh about him being an AWS guy and he's just started working in Azure. The more he works on Azure, the more he hates it. Is it the same with you, or is it only him?
Well, I don't have an opinion. Sorry, my dog just started barking because he's not happy with this presentation. But I've let him out now. So I'm not very opinionated about which cloud provider I like to work with in general. I think AWS is quite powerful, but Azure also has its own benefits. So on a case-by-case basis, you can evaluate which cloud provider meets your requirements, and then use that. As this solution says, you should never have a one size fits for all, and you should, because you have the benefit of choosing, you should choose based on what your use case really needs, if you can really. Okay, he says he was just kidding. So yeah, okay. Fine. Any more questions? No. Okay, so in that case, I'll reshare my screen and let's see whether these agents actually get terminated or what not. Can you see my screen?
Whilst that's updating, Vish, I've got kind of a quick question because for me, I'm on the opposite end of the spectrum, and I've lived in Azure since forever. But with these deprovisioning, one of the problems I've seen in Azure is that a deprovision of a VM, for whatever reason, unless it's inside a scale set, for instance, can take quite a long time to happen. So if you've got a massive amount of jobs like this, it could take, if you're not using scale sets, it could take hour plus just to
Okay.
deprovision. If you're doing a lot all in one go. How long on average are you seeing kind of deprovisioning in
Instant.
AWS?
So it is instant, and I'll show you what I mean by that. So as you can see out here, I'll go into Karpenter, and what Karpenter is doing is that it's corroding and deleting nodes in its own terminology. But whenever it sees nodes that are sat out there without any pods, it adds a TTL or time to live for 5 minutes, because I've put 5 minutes out there. But out here, as you can see, we've gone down from those 20 agents down to 2 or 3 agents. And in the background, if I refresh, those instances are terminated. So it's pretty much like instant. And it's not only the instance that has been terminated, but also the spot request has been canceled. So if I refresh this out here, you can see that you only have the spot requests active for the instances which are actually out there. And for the rest of the instances, the spot request is gone. And since the time that we spoke to now, most of these instances are terminated. And yeah, so long story short, it is pretty instant. Okay, so as you can see, folks, since we had completed all the agents and currently we don't have any agents running out here, ideally, what should happen and what happened in the background is Karpenter added a TTL to all of those VMs and EC2s, and those EC2s then thus got terminated. And we came to a point where we went from having 20 odd EC2s to support the 100 builds to terminating all the other EC2s. And currently we are sat on 2 EC2s as expected, because that's how much compute capacity is required right now to support basic workloads like core DNS. And if I go very quickly into AWS, and if I search by instance state, you can see that all the 2x larges, all the x larges, and all the mediums are gone. And the only 2 that are left are the T3 mediums, because that's the only thing that is required for powering the instances. And this was all taken care of natively by Karpenter. So yeah, I think at a very, very high level, that's how we have benefited from this solution. And we're currently looking at empowering more and more engineering teams within our enterprise businesses. But personally, I feel that this is a solution that is very unique and can support wider than just our enterprise clients. So I'm trying to reach out to the wider community to raise awareness of how the solution can help, and thus I've committed this back into my repository as well. So feel free to use that. If you go into that repository, it'll tell you everything that needs to be done, from creating a service link role to how to run the Terraform approves, and how to deploy your Helm charts, and how to deploy these Kubernetes manifest files. And yeah, in the future, I'm hoping to convert some of these Kubernetes manifest files into Helm charts so that it becomes even more simpler. But that is the end of the demo.
Oh, fantastic! Thank you very much, Vishal. That's awesome.
Thank you very much.
No worries. I hope you guys enjoyed, and if anyone has any more questions, then feel free to drop them to me on LinkedIn, or ask them right now, or get in touch with us anyways. But on that note, I'll hand over back to Liam.
Cool.
And thank you so much for the opportunity for me to present over here.
Thank you very much for making time out this evening to come and chat to everybody. Hopefully everybody found that useful. I know I certainly did, even though I've seen bits of it before. It's still interesting every time.
Yeah, it is very interesting stuff. I do like that.
So On to the final bit of business for this evening. And whilst Vish was just rounding out his talk there, I've run the prize draw and can tell you that Chris Chesney has won a JetBrains license for this evening. I'll get in touch with you over Twitter and send you your code. And all you need to do is redeem that on the website, and you'll be able to pick basically whatever product you desire for the next 12 months. And then when that 12 months is expired, you basically get a previous version perpetually from there. But yeah, so thank you very much, folks. You can join us again on May the 31st with our speaker to be announced. But if you are interested in speaking at DevOps Nuts as well, just get in touch. And on that note, I should bid you all good evening, and see you again next time.
Yep. Cheers,
All right,
everyone.
have a good evening.